So, hello everyone. Our name is Carlos Liqi, and we have been working at Intel as something very great. What we do is not including new features in Spark. What our team is doing, and we have been growing incredibly during the last year, is about improving the performance of Spark, but in a way that you guys have to do nothing to get it. Previously we were doing performance analysis for the JVM, and now we transition to work on Spark and Scala compilation and Spark compilation. And tonight we're gonna talk about something really important that talking last night with some of you, I saw it is quite important. And it is about GC poses, garbage collection. And sometimes for performance engineers like us, it's a pain in the ass. So we, at Intel, we are trying to fix that. And this is not something that is Intel technology. This will be shared with everyone. So without any more introducing, we'll let Liqi do the talking.
OK, so thanks, Carlos. We have been doing some practice trying to utilize the G1 collector, which is introduced after JDK 1.7 update 4. It's a pretty good collector, and we have some preliminary results. So I'm going to share the details with you guys today. OK, so why do we do this? There are two reasons. First one is Spark is a memory-aggressive framework. It tries to cache a lot of stuff in memory, and they choose JVM to be the host running it. On the other hand is that the hardwares that are currently available from all those vendors are keep increasing in the sizes and the speed. So we are having like more and more larger and larger memories on the system. So that's create one thing. It's like we're using heaps larger and larger, and we don't want GC pauses because they're unpredictable and if they're very long. So the application's performance, either response times or throughput, will be affected. And the solution currently is to find a very good GC algorithm to manage those large heaps. So there are already. We're going to share how we use it wisely. This slide shows what are the current available collector available in the JDK 8. The first collector is the parallel compacting collector. It is the default collector for all the JDKs after JDK 7 update 4. The flags is used parallel OGC in the command line. So you don't use any command line, you're using this collector by default. It's a throughput-oriented collector, which means all those GC pauses is stop the word pause. You collect your young generation, you pause your application. You collect your old generation, pause your application. There's no way you can do parallel concurrent collection through the time. The second one, the concurrent mark and sweep GC, is a low latency collector, means it tries to do some of the GC work concurrently with your application. This mostly happens when you collect the old regions. The good part is the latency for this collector most of the time is low. The bad part for CMS is it runs into this heap fragmentation from time to time. And when this fragmentation happens, you suddenly have this allocation failure out of nowhere because your heap utilization is low as well, and your allocation fails, and you falls back to this full GC, which is very long. That will kill your response time. And then there will be the new garbage first collector. It is also a low latency collector, which means you have some capability of lower the latency, and there are some other good promises as well. So here are the G1 collector promises we have. It has concurrent marking, similar to the concurrent mark sweep GC. So when application runs and you collect some part of your heap and marking those dead objects, your application doesn't need to stop. The second one is, unlike the CMS, where your old generation's objects are relocated in place, when G1 tries to collect some of your heap, it uses this evacuation fashion. So your live object will be copied to somewhere else. This naturally gives you some compaction of your heap, so you don't run into heap fragmentation that CMS suffered. And the simplified tuning part is like the design for G1 is trying to give you, use the G1 collector at your command line and then give a soft goal on the command line as well. That's it. It's not there yet, but we're getting really closer. So overall, G1 will give you very low and predictable latency. So since it's also packed your heap regularly, it's both throughput and low latency oriented. You can consider it that way. So following up, we'll do some overview of the architecture of the G1 collector, and then we'll give a case study about how we use these G1 parameters to tune it so that we can increase the performance of our Spark workload. So here is the garbage first collector overview. Some of you may already know about the CMS and parallel old collector, where you have these continuous regions called the young generation and old generation, maybe the perm generation. In the garbage first collector, we don't have this continuous region anymore, even though we still have some part of the heap designated to the Eden and the survivors and the old objects. The heap is divided into 2,000 approximately same-sized fixed chunks, which are called regions. And each region can be tagged as Eden region, survivor region, old region. And those tags can change, depends on the lifetime and the runtime of your collector. And that 1 meg to 32 meg is currently what the available region size. There's another tag that doesn't happen before-wise, which is called the Humongous region, where you have this very large object, and the size of the object is larger than half of the region size, and the collector decides to choose it differently. So the humongous regions are handled like an old region, and is treated differently. So the number of regions inside Eden and the survivor may be adjusted, which indicates that there are some heuristic and smart movement in the runtime of this G1 collector to adjust the heap layout and try to make sure that it runs very efficiently. So that covers all the heap layout, and there are several types of collection cycles that we can cover. The first one is the young GC, which similar to the young GCs in parallel old and CMS. You allocate your objects in Eden regions, and then gradually your Eden region fills up, and there will be some allocation failure. You do an Eden region collection, which is called the young collection. You copy all the survivors to the survivor regions, and then third time, if the objects survive several cycles of this young GC, it will be promoted. And those humongous objects, they will bypass this young GC and be allocated directly to the humongous regions, and it will be handled in the concurrent phases that we are talking about next. So the concurrent marking and cleanup phase is trying to collect the dead objects in the old region and the humongous region as well. It is the concurrent marking and the cleanup phase so that your application most of the time doesn't need to be paused. And this is very important because it identifies what are the objects are dead in your old and humongous regions. And after this concurrent mark and cleanup phase ended, we'll have a very clear view of what are the regions inside the old and humongous regions are most filled up with the dead objects, which are garbage. So the top several old regions will be combined into the collection set of the next several young GCs to make the young GCs collect both the Eden regions and the selected old regions. Then that GC cycles will be called a mixed GC. Mixed GC will collect your old region, so it is very important because it compacts your old region so that we don't run into heap fragmentations. And finally, if all of those 3 cycles doesn't work, you fall back into this full GC, which is a serialized GC and takes a very long time to finish. Right. So here are some parameters before we start the tuning. On the left side, we have a G1 GC diagnostic flags, where we can collect a lot of useful information in the runtime of the collector. For example, collect whatever the JVM is providing at the start time about the parameters you can set. The print flag is final. The good news for this flag is that from different version of the JDK and different release, those default parameters may change. And it gives you a very good view of what parameters have been changed so that we don't have any surprises. And print GC details, very important. That's all the information comes from. And GC date stamps and GC timestamps gives you date and time and relatively timestamp of when this GC event happens. And then print adaptive size policy gives you a very clear view of if the collector tries to do something and adjust the heap layout. And you can see that in your GC log. Then print references GC. It's like there are several types of software references that garbage first collector is trying to deal with. Some of them are not very easy to deal with. So if you look at the references processing time, they'll give you some clue about if anything goes wrong with the reference processing. On the right side, we have this performance flags. Use G1GC and the heap size, and we always enable this parallel reference processing because it's good to speed up this the process process. And then you have this soft goal called the max GC milliseconds. It is a soft goal means that it tries to tell the garbage collector what kind of GC pulses you are targeting at. It is not a guarantee. So most of the time you set this maximum GC pulse soft goal to about like 100 milliseconds, and maybe you'll get 70% of your GC pulses above that. That is normal. It's just a soft goal that tells GC, try to meet that thing. And then there will be a parallel GC thread. This parameter says how many GC worker thread in the runtime you want to do in the stop the work GC collections. Oracle JDK has this formula to calculate how much is appropriate for a specific system. We try to fix this in the front so that we don't have any surprises if the Oracle JDK tries to adjust the number of this worker threads. Okay, so a little bit overview of our experiment environment. It's a pretty small cluster. We have 4 worker nodes, Xeon E5 processor, which is pretty powerful, 192 DDR3 RAM, 10 gig Ethernet. And software-wise, we have very late Oracle JDK and pretty new kernel. And we're running this graph computing workload from our customer. It tries to compute a n-degree weight table and truncate the topmost weighted vertices as your output. Okay. I don't think the slide is updated, but well, yeah. So we use the Java serializer, and we don't try to use the cryo serializer. That's not correct. And we use 128 partitions. So that being said, and let's get a little look at how this data looks. We try our baseline run, and here are the GC pulses we get from the GC logs. Apparently, we have some issues here. So there are 2 GC pulses that are very long in the upfront. One is 107 seconds. The other one is 91 seconds. Those are like single-threaded full GCs. And the total execution time for this is 470 seconds. And we have 63% of the execution time spending in those GCs. That's not very good. Okay, so here comes like what do we do next, right? We get the data and we see there's a problem. It's very typical to see what the GC logs showing us, try to look for those outliers in the GC logs so that we know what are those full GCs or very long GC pulses happens. And then we understand what is the root cause for these GC pulses so that we can try to figure out what we can do to make the GC works better. And then we can carry out the experiment to try out our tuning parameters. And then if necessary, we can repeat these steps over and over again till we actually meet our performance target. All right, so let's first look at our GC logs. Those are the GC log from one of those worker nodes, and it has this 107-second GC pulse. So from the heap ergomatic, you can see that when this GC happens, before the GC, we have 97.3 gigabytes of objects living on that heap. And after it, we have only 53.9 gigabytes. So apparently the full GC is very efficient, and it looks like we have a lot of garbage piled up in our heap when this full GC happens. Right, 45 gigabytes of non-used objects. And then, all right. Okay, so this GC happens at 175 seconds after this GVM is launched. So we have good news and bad news here. The good news is this is a normal full GC. We don't have any weird things going on. It's a GC object allocation failure trigger GC when we're actually trying to allocate an object and we don't have any space, so that it tries to expand the heap a little bit, but it failed, so that we have to do a full GC and pause the application. The bad news is that we have a lot of garbage piled up. Okay, so let's take a step back and look what happens before that full GC, and here's what we found. 35 seconds before that full GC, which is 140 seconds, the G1 collectors decided to do a concurrent cycle. So we see that for 140 seconds, you have this GC concurrent mark start. And then after that, we see time minor GCs inside the same GC log. And after this full GC, we see a concurrent mark abort, which means the concurrent mark phase didn't finish, so that the heap fills up with garbage and the full GC has to kick in. All right. Okay. So here's the root cause and what we are proposing to the solutions. The concurrent marking phase doesn't finish in time, so that we don't have any clue of what are the garbage in the old generation. We only do young GCs. Remember that when you do young GC, you only collect part of your heap, which is the young regions, and you try to promote some of those survivors that has reached the aging limit, so that they're promoted into old region. So once you have this consecutive minor GCs, what you typically see in your heap utilization is your old region is keep expanding, and your young region is a fixed size, so that your heap utilization keeps growing when you have this consecutive minor GCs. The heap only reduced the heap utilization when this concurrent marking phase stopped, and all those dead objects in the Humongous and old regions have been identified, so that you can do this cleanup where all the regions that doesn't have any live object will be cleared up, so that will be freed. And then those identified old regions with a lot of garbage, they will be put into the next several minor GCs to make them into mixed GCs, so that we compact and collect or old regions. So that being said, we have to make sure this concurrent cycles is fast enough so that we don't hit the heap growing problem as we saw in the previous slides, so that we have minor GCs promoting things into old region, but we also have this concurrent and cleanup, and then we have mixed GCs to reduce the heap utilization from both the young and old regions. There's a parameter that we can choose to tune, which is the concurrent GC threads number. This is different from the concurrent worker thread that we set in the front. That number is trying to give you a clue of how many GC worker thread you want to use in the stop the world GCs. And this concurrent GC thread is configure how many concurrent threads you want to use in your concurrent marking phase. So apparently the work is almost fixed, but if you have more workers, you can definitely speed up it a little bit. Okay, so we threw out the new GC tuning parameters in our command line, and we launched the same workload again. This is what we see after the tuning. So apparently, there's no full GCs anymore. And the total execution time for this workload reduced from 470 seconds to 217 seconds. And we only spent about 27% of time in the GC, which is somewhat acceptable compared to what we had before. Okay. All right. So here is the comparison before and after this tuning. we see that if you look at those orange dots, at the after the very long GC pause of this full GC, there's nothing going on inside the system because on the entire system, there's only one thread that is the full GC thread running. You don't have worker thread of your Spark. You don't have other GC worker thread tries to sweep the heap. Only one thread is doing GC. So by reduce that kind of GC pauses, we actually have this. So what we're trying to compare here is there are different GC pauses in garbage first collector, and it's a very good way to see what those different type of GCs is distributed through the run. So before the tuning, we have a lot of young pauses. We don't have too many mixed GCs, and we don't have many cleanup. We don't have many remarks, and we have full GCs. That is very bad because it seems that we're trained very aggressively on the young regions. We don't really care about old regions, which we really should care. So after the tuning, a lot of GC have been moved to mixed GCs. We actually see like 5x more mixed GCs compared to the baseline. And apparently, we don't have any full GCs anymore. And the total GCs pulses is reduced about like 30 to 50%, if I remember correctly. All right, so conclusion-wise, we're using JDK8's update 60. I think it's available at least for the early release for Oracle JDK site. It looks like the G1 collector works pretty well for large heaps, at least 100 gigabytes. The default GC parameter still doesn't do very well on this because it has misconfigurations that doesn't suit this large heap and Spark's aggressive memory allocation stuff. So it requires a little bit of tuning. And if you tune it a little bit, it will have this low GCs and low GC pulses and very good throughput after all. Okay, so if you have any questions or you have any opportunities in GC tuning, please contact us. And I think that concludes our presentation. Right, and here are some resources that you can get started with using G1 GC. Oracle engineers have a lot of very good articles describing how you can tune this thing and how GC internal works. Okay, I think we ran very ahead of time. Yeah, so question time. Any questions so far?
So meanwhile we get any questions, I want everyone in this room to think about one thing and one thing only. And it's that if you remember, for those playing with Java 10 years ago, Java garbage collection was never designed to take 50 gigabytes of heap and take it off the stack in one stop. And what we're trying to do is our team is trying to bring new technologies like the G1 garbage collection, optimizing that collector so you guys can use it out of the box. And this is what we're trying to do. We are trying to bring future usage to Java garbage collection, which is quite a challenge, by the way.
Okay.
Anyone has a question? Mike?
Based on the talk, what I could see is that the only tuning parameter that you've used to get the GC time down was the number of threads for the parallel GC. Is there any other tuning that could be done to the G1 that could help, or have you experimented with other parameters as well?
Oh yes. So basically, since we only identified these only problems that we run into full GC, but I think I've done a talk on the HBaseCon about how to tune HBase towards the low latency part. There are several parameters you can tune. For example, the initial heap occupancy to start the concurrent phase by default is 45%. And that controls when you want to start your concurrent phase. If your concurrent phase starts very late, even though you have a very aggressive number of concurrent worker GC thread, probably your concurrent phase is not very paced with your other cycles too. So that thing is one parameter. The other is like when you actually do mixed GCs, there are some parameters showing how much you want to scrap from the collectible regions. And that is like a heap waste percent, if I remember correctly. That gives you a clue about, like in the mixed GCs, what is your collecting target about how much of those regions you want to collect. For example, by default, the heap waste percent is 5%, so that as long as there are more than 5% of collectible objects, the mixed GC will continue. And mixed GC takes a lot of time comparing to the young GC because they try to do a lot of lab object tracing using the remember set and do reference processing. So that is one thing. If you want to reduce the overhead of mixed GC and you are sure that you can tolerate a lot of garbage, then you can increase that heap waste occupancy, heap waste percent, so that you can cancel some of those unnecessary mixed GCs. And there are also some other parameters like what kind of criteria you want to identify a region to be garbage filled up. There's a parameter showing that above this percentage, I want to identify this region to be garbage collectible so that I can combine them into the mixed GCs. And I don't remember exactly what the default parameter is, but I can send you the parameters afterwards. Let me see. And right, so we already covered the reference processing so that we enable this parallel reference processing already. There's some other thing you can do is some of the time if you have your GVM running for a long time and your object allocation rate is changing from time to time. For example, when you have your service really busy, you may have many objects allocated and die. But if your GVM runs overnight and during those less busy times, probably the object doesn't die that quick. And there are some situations where GVM tries to resize your young generation because you give them a soft goal and the GVM thinks, okay, I'm meeting this soft goal perfectly so that I can do more and I increase my young generation sizes. And we actually see there are sometimes you have 30 gigabytes of young generation in your G1 collector, and suddenly something kicks in, and there's a very long young generation pulse as well. So fix the new size percentage to some like 1, 2, 3, 4%, depends on your heap size, that you don't have very lengthy young generation pulse as well.
Comprehensive. Oh, thank you very much for the comprehensive reply.
All right. The question is the G1 the recommended algorithm for Spark streaming application as well? And if so, is there any tuning specifically applicable to Spark streaming?
So the question is about Spark streaming garbage collector parameter suggestions, right? We haven't do too much streaming works. So first of all, we need to find out a representative Spark streaming workload. If you have your GC logs ready, we can take a look at them so that we can at least figure out what is most suitable for your workload. And then probably if we can get a lot of GC logs and runtime models, we can get some GC tuning BKMs for Spark streaming as well.
More generally, do you recommend the G1 GC for Spark rather than parallel or CMS GCs? Because there is a discussion going on in the OpenJDK community whether to make the G1 GC as a default collector or not.
So currently the parallel OD and CMS is in bug fixing cycles, which means they're not being improved anymore. And all those efforts that OpenJDK community and Oracle will put into improve this G1 GC. So my suggestion is if you don't have any problems with your current GC, for example, you already have a BKM for tuning parallel OD or tuning CMS for different type of your workload, stay with them for a while because G1 is still improving and there's still bug fixing and feature added to it. If you have trouble that you don't think parallel OD and CMS can cover, then it's worth a try to use G1. Because I know some of them are still use like a GDK 6 or even GDK 7. The G1 collector is usable or semi-optimal choice at very late stage of JDK 7. So if your JDK is pretty old and stable, stay with whatever you have. And if you are trying to use new JDK, it's a good time to start with the G1.
Thank you.
Okay, so.
Yeah, I have a quick question. So regarding data frames and Project Tungsten, do you think that will improve performance with GC or any benefits for GC?
I think it depends on your heap configuration and what you actually use your heap after you embedded the tungsten inside your workload, your framework. If you still have a very large heap and you allocate a lot of stuff on it, then probably you still need to do something on the GC side. Or if you are trying to use tungsten and with a very tiny heap, probably you don't need to worry too much about GC. So it depends on your runtime configuration and stuff. I didn't quite figure out. Okay. I think we can take it offline so that.
Yeah, sorry. So what about data frames?
I'm not very sure because I haven't looked at the data frames GC models yet.
Okay. Thank you.
Thank you.
Thank you.